There is a 248-dimensional object that took a supercomputer 77 hours to fully describe, produced an answer larger than the entire human genome, and may be the secret operating system of the universe. Mathematicians named it E8. And to understand why anyone built it, we have to start with something embarrassingly simple: spinning a hexagon. Here's a question that sounds dumb until you actually try to answer it. What is a symmetry? Most people, if you ask them, will say something like when a thing looks the same on both sides. Fine. But that's a description of a property, and properties are boring. The mathematician's insight, the one that cracks this whole field open, is that a symmetry is not a property of an object. It's an action you can perform that leaves the object unchanged. That sounds like a meaningless distinction until you watch it pay off. Take a hexagon. I can rotate it by 60 degrees, and it lands perfectly on top of itself. You couldn't tell I'd done anything, which is the entire point. It's the perfect crime. I can rotate by 120, 180, all the way around. That's 6 rotations. I can also flip it across any of 6 axes. Add those up and you get 12 different actions, each one leaving the hexagon looking identical. Mathematicians call this collection the dihedral group, and group is just the technical word for a set of actions you can combine. And combine them you can. Do one rotation, then another, and the result is also a rotation in your set. Every action has an undo. There's a do-nothing action, which is the symmetry equivalent of getting up to grab a snack and sitting back down. These 3 properties, closure, inverses, and an identity, are the rules of the club. Memorize them or don't. The universe doesn't grade on this. Now here's where it gets interesting. The hexagon gave us 12 symmetries. 12. Countable on your fingers, with 2 left over for emergencies. But what happens if we smooth off the corners and make a circle? A circle doesn't have 6 rotational symmetries. It has all of them. Rotate it by 1 degree, by half a degree, by 0.0001 degrees, by some irrational number of degrees that would make your high school teacher cry, every single one works. The symmetries are no longer a tidy little list. They form a continuum. And this continuum of rotations has a name, SO2, the special orthogonal group in 2 dimensions. Don't worry about the name. Physicists name things to feel powerful. Here is the genuinely beautiful part, and I want you to sit with it. Each rotation of the circle is labeled by an angle, somewhere from 0 to 360 degrees. And the set of all angles from 0 to 360, wrapping back around to the start, is itself a circle. So SO2 isn't just a set of rotations. SO2 is a circle. The group is a shape. Let that sink in. The thing you use to transform a circle is, geometrically, also a circle. And combining 2 rotations, doing a 30-degree turn then a 50-degree turn, is just adding their angles to get 80. Group multiplication became addition, and the whole operation traces out a smooth, continuous path along that circular shape. No corners, no jumps. This is the defining feature of a Lie group, named after Sophus Lie, a Norwegian mathematician whose name is pronounced Lie, not Lie, which is the only thing in this video that's pronounced sensibly. A Lie group is 2 things welded together: a group, where you can combine and undo transformations, and a smooth manifold, which is a fancy word for a shape with no sharp edges. The elements of the group are points on the shape. Combining elements is sliding around on that shape. Let's bump it up a dimension, because 2-dimensional rotations are a toddler's toy. Consider all the rotations of a sphere in 3-dimensional space, SO3. How many numbers do you need to specify 1, 2 to pick the axis you're spinning around, and 1 more for how far you rotate? 3 numbers. So SO3 is a 3-dimensional manifold, a shape living in some higher dimensional space that I cannot draw and you cannot picture, and we will both pretend that's fine. The point is that the entire chaotic universe of possible 3D rotations, every tilt, every spin, every way you can fumble a Rubik's Cube, is captured by smooth movement along a single geometric object. Spinning things in your hands is, secretly, a walk in the park. A 3-dimensional, mathematically abstract park. Now we do the move that makes Lie groups genuinely magical. We zoom in. Pick one special point on the group, the identity element, the do-nothing rotation, the snack break move. And just like zooming into any smooth curve makes it look like a straight line, zooming into a smooth manifold near the identity flattens it into a flat space, the tangent space. And this tangent space at the identity has a name that has terrified undergraduates for a century, the Lie algebra. But it's not scary. The Lie algebra is just the collection of infinitesimal symmetries, the tiniest possible nudges away from doing nothing. Think of it as the DNA of the group. For SO3, this tangent space is 3-dimensional, and its elements correspond exactly to axes of rotation. Tiny rotations around the x-axis, the y-axis, the z-axis. These are the building blocks, the so-called generators. Everything else is built from them. And how do you build a full rotation out of these infinitesimal nudges? You repeat a tiny one over and over and over. The mathematical machine that does this is called the exponential map, and if you remember that e to the x can be built from repeated tiny multiplications, you already understand it. You take an arrow in the flat tangent space, a direction and a length, and the exponential map unrolls it into an arc on the curved group. A straight little vector becomes a genuine rotation. The DNA expresses itself into the full organism. So this is all gorgeous, but you might reasonably ask, who cares? Why does anyone outside a windowless math department lose sleep over the shape of a rotation group? And the answer comes from a woman named Emmy Noether, who in 1915 proved a theorem so important that physicists genuinely should put her face on currency. Noether's theorem says, every continuous symmetry of a physical system corresponds to a conserved quantity. Read that again, because it's doing an enormous amount of work. If the laws of physics don't change when you rotate your experiment, and they don't, the universe doesn't care which way your lab faces, then angular momentum is conserved. If the laws don't change when you slide your experiment over by a meter, then momentum is conserved. If they don't change from one moment to the next, then energy is conserved. Stop and appreciate the audacity of this. Conservation of energy, the bedrock principle that powers every engine, every battery, every smug physics teacher, is not a separate law of nature handed down on a stone tablet. It is a consequence of the fact that time has a symmetry. And those generators we found in the Lie algebra? They literally are the conserved quantities, up to a constant. The DNA of the symmetry group and the conserved quantities of physics are the same object wearing different hats. Physicists looked at this and said neat, which is the strongest emotion they're legally permitted to express. So Lie groups aren't decorative. They're the grammar of physical law. Which raises a wild question. How many of them are there? Can you just invent any symmetry you want? And here is one of the most beautiful results in all of mathematics. Two men, Wilhelm Killing and Élie Cartan, working in the 1880s and 1890s, set out to classify all the simple Lie algebras, the indivisible atoms from which the others are built. You'd expect the answer to be infinitely many, in messy infinite variety. Instead, they found something almost suspiciously tidy. There are exactly 4 infinite families, labeled A, B, C, and D, because by then everyone was exhausted, plus exactly 5 weird exceptional ones that don't fit any pattern. G2, F4, E6, E7, and E8. That's it. That is the complete list of fundamental symmetries available in mathematics. Each one gets a little stick and dot picture called a Dinkin diagram, and together they form something that looks unsettlingly like a periodic table, except where Mendeleev's table eventually runs out because atoms get unstable. This list is provably complete. 5 exceptions. Not 4, not 6. 5. Mathematics drew a hard line in the sand and the universe respected it. Which brings us, finally, to the monster at the end of the book, E8, the largest exceptional Lie group, and a 248-dimensional object. Its structure is encoded in something called a root system, and that root system was so complex that fully mapping it required a team of mathematicians and a supercomputer crunching for 77 hours, producing a result that, written out, is larger than the human genome, to describe one symmetry. And when you project E8's root system down into 2 dimensions, you don't get noise, you get a staggeringly intricate, perfectly symmetric mandala. Hundreds of points arranged with a precision that looks deliberately designed. It is arguably the most beautiful object humans have ever discovered. And we discovered it. We didn't invent it. It was just sitting there in the logic of mathematics, waiting. Here's the kicker. In string theory, one leading candidate for the symmetry group of the entire universe is E8 cross E8, meaning this monstrous, gorgeous, 248-dimensional object that took a supercomputer 3 days to describe might be, quite literally, the shape of reality's symmetry at the deepest level. So let's zoom all the way back out. We started by spinning a hexagon, and we ended at a possible operating system for the cosmos. And the thread connecting them is this single, mind-bending idea. The universe does not merely have symmetries. Symmetry is the universe's source code. The laws of physics aren't restrictions imposed on nature from the outside. They are consequences, direct, unavoidable consequences, of which Lie group nature happened to choose. Energy, momentum, angular momentum, the forces themselves, all of it falls out of the shape of symmetry. Not bad for a subject that started with somebody refusing to accept that a hexagon was finished spinning. If this gave you that pleasant feeling of the universe quietly clicking into place, subscribe to Improper Integral for more visual math and science, and we'll see you in the next one.